Good idea to put up a slide warning you there might be some IBM jokes. Of course, I guess this isn't really IBM country out here, although I did hear a rumor that you still programmed in Fortran quite a bit, and even the dread word COBOL was heard, so maybe it's worthwhile. You know, object-oriented programming is actually a rather old technology. It is just a few years younger, in fact, than the kind of programming technology that most people are used to, that of data structures manipulated by procedures. And for various reasons, it has not come into currency, into vogue, until the last couple of years. But it's actually about 25 years ago. I wrote my first program that I would call object-oriented in 1962. And people have been writing programs in that style even earlier than that. In my particular case, I was a programmer in the Air Force at Air Training Command. In 1962, there were no standardized operating systems. Of course, that's true today. But back then, there was actually a reason for it. Nobody had gotten around to the idea of thinking it might be useful, and Air Training Command had a problem of moving tapes with records of various kinds on them from one Air Training Command base to another. The machines back were Burroughs 220s, which were machines that had about 5,000 characters of storage, were about the size of this room, and were great coffee warmers. My image of them, of the 220, is with this huge set of boxes with a row of pots on top, trapping the heat as it came out. Now, the problem that they had was that there was no way to standardize on what the formats of the different records were. They changed, and the operating system was usually just a kind of a loading program, and so there was no way of standardizing on that. And they wondered, how can we actually read these data records if everything is constantly changing and nothing holds still? Somebody thought up a great idea. That idea was to have the records shipped in the following format. Each tape file had 3 sections to it. The front section was fairly short. It had a bunch of relative pointers into the second section, which contained a bunch of Burroughs 220 code. And that code knew how to deal with the third section, which had the actual data records. And so what you got when you read a record from this machine was you read that record, the first 2 parts of the record, into storage, used the front part of it, which were these indirect jumps into the second part of it, the code, as the protocol for dealing with the tapes. There are usually about 20 or 30 what we would call messages today, but 20 or 30 entries in that first table. And the code that came along with the tape records knew how to deal with all the data. So in current day terms, what the Air Training Command was doing, I think it was as far ago as the late 50s, was to ship an entire class of objects. The class was shipped with the protocol, with all of the code, and with all of the data in a form in which you did not have to penetrate any of it in order to make use of it. That was used for a number of years as a technique until COBOL came in and the Air Force forced all of those good ideas to go away in order to standardize on COBOL, which is a much weaker conception, going back to the notion of data structures that are fragile. Now, I understand that we have a kind of a mixed audience today, in that some of the people in the room are rather knowledgeable about object-oriented programming. Some of the people in the audience are here out of curiosity. So I made a kind of a mixed talk. What I would like to do is to give you sort of a perspective on where object-oriented programming has been, what it's been done, without getting too historical about it, but try and give you an understanding of why it has contributed so much in a number of areas other than just writing programs that don't break. One of those is user interface, which is a very important area, and there are some direct relationships to the way we think about objects and to the way we think about user interface. And then take you into the future a little bit and show you some of the things which object-oriented programming is being used for in research directions, and then try and open up the forum into issues, because my belief is that the basic ideas of object-oriented programming are quite simple, maybe too simple to be popular until we absolutely require simplicity in this stage of 2 million line programs. But that the most interesting thing about object-oriented programming are the various issues and the styles for using it, and those haven't settled yet. So my reference to the IBM joke, I think a good way of starting out the talk is that last year, it was even reported in Business Week as a significant event, IBM had its first object-oriented colloquium. It was such an amazing thing. They believed that only 25 people would attend, and in fact 500 attended, and they had to turn away 500 people from within IBM. I got invited to give the keynote talk. Part of what I'm going to show you today is from that keynote talk, and standing there in Yorktown Heights giving the talk, I was reminded of William James's characterization of the 3 stages that an idea goes through. The first stage is the new idea is characterized as the work of madmen. It's absolutely denounced, out of hand. And a few years later, goes through a different stage when it's remarked on as being commonplace and obvious all the time. And then the third and final stage is when the original denouncers claim to have invented it. And we're now in that third stage for object-oriented programming, because now that IBM has decided to adopt object-oriented programming, we can be quite sure that it's actually obsolete and on its way out. So now, before I get into the historical part, what I thought I'd do is, for those people who are not acquainted with it at all, I thought I would just say a couple of words about what I mean when I say object-oriented programming. And I have a very simple diagram here. For me, the whole notion of objects was triggered off by seeing a number of different systems, some of them in computer science, but the first ones that I looked at were actually biological. I have a degree in molecular biology, and one of the things that struck me when I was studying molecular biology many years ago was that compared to the kinds of structures that we tend to build here on Earth, the average biological structure is more than 1,000 times as complex, both as regard to the number of different parts it has and to the complexity that has to be controlled. For instance, a grand piano is a rather complex machine, has about 20,000 parts, which surprises most musicians who don't even think that they're actually playing on a machine. They think of it as an instrument, and an instrument by definition can't be a machine, but in fact it is a machine. Has about 20,000 parts. Our bodies have approximately 1 trillion cells in them, and each cell is rather complex. Each cell has many millions of components in its own right. So one of the ways nature discovered to control complexity and the kinds of interactions that are likely to happen is to try and encapsulate them in various ways. This is a familiar principle to us. It's something that we use in regular programming as well. Try and encapsulate. And the question you're always asking when you encapsulate, we're going to ask this quite a bit later, is just what is encapsulated? What kinds of things are we trying to control? Now, usually in regular programming, what we encapsulate are sections of programs, and occasionally we'll try and encapsulate with regard to a protocol for dealing with some system we don't want to inquire about the internals of. What biological systems encapsulate is the actual environment in which most important processing takes place. There are very few object-oriented programming languages that go that far. The average object-oriented programming language encapsulates not the environment, but in fact something like the state of a data structure along with the procedures that know how to intimately manipulate it, and try and tie those two areas together in a way that they cannot be penetrated from the outside. When people speak of an object-oriented programming language like Objective-C or C++, they're talking about even less than that, because there the encapsulation is almost a convention. It's done by means of macros. The amount of protection at runtime that is delivered is rather low. So there are all of these gradations. Now, biological systems encapsulate with a vengeance, because nature discovered that if you give each cell its own little captured ocean and let it devote about 90% of its actual energies to simply protecting itself from the outside world as though the outside world were hostile, then you get a situation where you can build very large structures rather safely. And encapsulated is not just the saline solution, not just the organic molecules, but also encapsulated and not just the programs that drive the cell, but in fact encapsulated in biological organisms, as many of you are aware, is the entire plan for the entire structure. Okay, now we don't generally do that when we write an object-oriented program, but in fact people are starting to do that now in artificial intelligence, and people who are interested can bring this up later. So my particular motivation when I started thinking about objects was simply that of biological cells. And one of the things that is difficult to escape when you look at biological cells is, first, the extent to which the outside world is kept away from the cell membrane. And then the other thing is that the cells aren't completely in isolation. They communicate by means of sending messages to each other. And again, the way we translate that into computer terms is done in a much more restrictive way than biology does it. Biology generally communicates without worrying who's going to receive. And I'm going to talk a little bit later about a object-oriented strategy in which messages aren't sent at all. They're only received. You might think about what an object-oriented system might be like if you never sent a message but objects could receive. What would they receive if all they could do is receive? The translation of this model into machine terms, for me 25 years ago or so, was that these biological cells acted a lot as though they're on a network. You can think of it as a crossbar switch or a Ethernet type network in which every object can send to every other object. And each one of these things is a lot like a little computer. In fact, it's very difficult in a good object-oriented system to find out where the hardware stops and the software begins. And this notion of a little computer in the large here is something that is worthwhile considering when we think about making very small things. Now there's a principle in design that people came up with many years ago. It's called the basic principle of recursive design, and the idea is make the parts have the same power as the whole. We know in the factorial example that a recursive program like factorial, its charm is it's able to re-invoke itself as one of the conditional branches. And so in some sense, the program remains, as long as that is true, the program remains as strong as it was when you entered it, because you can always re-enter it instead of getting diluted away. Now another thing that, that crossed my mind when I was pondering these ideas back in the 60s was, why, if that is such a powerful idea, why is it that we take a very powerful idea like a computer and dilute it immediately in most programming languages by dividing it up into data structures and procedures? Data structures don't have the same power as a computer. They're static, can take on marks, but they're, once you get a data structure, it just sits there. Procedures don't have the same power as computers because they can't remember state. They have to have something additional. So what we did in the guise of following standard mathematical notation in the 50s, when Fortran was developed, was to mimic standard mathematical notation without thinking about this basic principle of recursive design, because people didn't write recursive programs back in the 50s. And so the baby is thrown out with the bathwater almost immediately in a standard procedure and data structure language. And it occurred to me and other people who were thinking about these ideas back then, what if you didn't do that? What if the only subdivision you ever made in a programming language was a subdivision of a computer into a computer? You're never allowed to subdivide the computer into something that was less than a computer. And what does that mean? That means that each subdivision has to be something like a black box that has inside of it some mixture of state and process. From the outside, you can only invoke behavioral attributes rather than invoking method attributes. And what I mean by that is, this is something that was even in Fortran, because the earlier designers of Fortran realized that there was a very funny correspondence between procedural things and data structure things. So for instance, when you say sin parenthesis 30 close parenthesis in Fortran, you can't tell by looking at that whether you're invoking a function or whether you're accessing an array. And that was not accidental back then, because of course they thought of arrays as being a kind of a function, and they wanted you to be able to write arrays, huge tables, still done today, in order to do functional evaluation very quickly. What they didn't realize is that you wanted to be able to trade off between the two. But that notion of just saying sine 30 degrees without indicating how it's to be computed is the essence of the kind of abstraction that object-oriented programming is all about. It's carried very far here by this strong membrane of the object, so that what we're dealing with here are behaviors, and there are two important implications that had to be worked out early on. One of them is that messages, in most cases, can't be commands, or you're violating the notion of the object as being in control. Now, most object-oriented systems today, when you do what is called sending a message, you are issuing a command. Objective-C, C++, even Smalltalk 80, all of those systems, a message is actually something very, very close to, if not identical to, a certain kind of procedure call. Okay, but in fact, in the original scheme, and we can talk about the implications of why this is a good idea later, in the original object-oriented systems that were so successful, messages aren't commands at all. What they are desires. I'd like to have this happen. Just to give you an example of why, imagine we have an object masquerading as a critical system file. And the question is should just anybody be able to come up and issue the command to it, turn byte 5 to 0? Now, it's done all of the time, but in fact, in an object-oriented system, you would like the object to be able to protect itself so that even a person who has a pointer to it, even a person who has the knowledge of which command is the right command, that both of those do not imply that you have permission to actually change that file. So when I talk about an object-oriented system, I mean an object in which the worst you can do to an object is to simply indicate to it that you would like it to do something for you. And the best that can happen is it will do that. The worst that can happen to it internally is it will simply refuse. It may take your name and give it to the principal later if you've done something wrong. But so this notion of absolute control, that messages can't be commands. And the other one is because the object is no longer a data structure in any sense that we regard it, that assignment is something that can't be done from the outside either. So the assignment statement has to go away in the form that we know it as an irrevocable change to a variable or a slot in a data structure. An assignment has to be changed by something that we can think of as being advice or influence. So again, this notion of getting an object to change its state is something that we normally don't do in object-oriented programming, because normally in object-oriented programming we are not simply trying to imitate data structures. Now, to me, a data structure is that thing that if you send it to somebody else, you're giving them permission to change it. That's what I mean by a data structure. So it's clear that some of the things that we call data structures in normal parlance in a system with an operating system that offers some protection are not strictly classical data structures by that means. Certain files usually have protections on them so that in a good operating system, when we send a file from us to somebody else, we are not conveying to that person the same level of protection necessarily that we have been granted. So in a good operating system, this may be an operating system that you've never seen, but there have been operating systems in the past, and there exist operating systems now, so that if you have a certain set of permissions for a file A, and you wish to give this file to your friend, suppose you have the magic permission to change any byte in the system file because you're a honcho, then you might wonder, should I be able to pass on those permissions to the next person that I give this file to? The answer in a good operating system is no. Each person should get their own permissions separately. And when they receive this file A, it's their permissions that are granted by the operating system that obtain, not the permissions passed on to them by somebody who had the file before. So you can think of taking this desperately important file, passing it along, and when it goes to somebody who is less to be trusted with it, they have fewer permissions on it. There are fewer things that they can do with it. And then if they pass it on to somebody again, that may go back to a trusted person. That person should be able to re-invoke those operations that were taken away. There's a whole set of schemes for doing this that is called capability protection. And capability protection is, again, another one of these old ideas from the 60s, intertwined in a very strong way with object-oriented design that is now coming back. Capability is simply a technique for protecting objects in a stronger way than normal digital computers allow them to be done. And again, at the end of towards the end of the talk, we'll talk a little bit about this. So to me, there are lots of different ways of talking about objects, but probably 90% of the reason, to me, for dealing with objects at all has to do with their abilities to protect in various ways. Protect by encapsulating various kinds of things, almost always state, less often control is encapsulated, and so forth. And then about 10% of the use of object-oriented programming, to me, has to do with its ability in whispering to you how you might design a system better. And just one more note about that before I get started on the talk proper, and that is that the way objects are used today is a little bit confusing because they're intertwined with another set of ideas that came out of the 70s that are very similar, particularly in implementation these days, and that's what's called data abstraction. How many people are familiar with data abstraction as an idea? Okay. So data abstraction looks a lot like object-oriented programming, but its intent is different. The intent of data abstraction is to take a system that you're familiar with, like Pascal or Fortran, that is starting to run into difficulties of various kinds. The difficulties are usually representational ones. I think everybody's had the experience programming in a language with data structures. You get this big system done. You decide you need to change your representation. And the next thing you know, you're hunting down all of the procedures that think they knew about the old representation. And the rule of the universe is that there's always one or two that you don't find. So you slide in the new representation, and a couple of months later, one of those procedures is invoked, and all of a sudden you have a crash, and people wonder why. The answer is the critical knowledge has actually been spread out in such a way that it can't be recovered. It's like what you have to do after you do a multiplication. In order to recover the operands, you have to do much more work. It's like the difference between differentiation and integration. The same thing is true, is once you've lost information in a system, once the entropy has gone up, then it's very hard to get it back. So one of the things that you try and do with objects is to try and maintain as much informational content as you possibly can in as small a place as possible. Now, data abstraction techniques use a similar way of wrapping an envelope around a data structure and invoke operations by means of procedures in order to try and get to be a little bit more representation independent. The difference, though, Ada, for instance, is a language that is a data abstraction language. It's not an object-oriented language. And even the people who actually understand Ada don't claim that. But you can do certain kinds of things that are now today called object-oriented in Ada. So this envelope of procedures is wrapped around the data structure in an effort to protect it. But then what happens is that this new structure that's been created is then treated as a data structure by all the rest of the program. The result is, particularly in Ada, is that the programs are not small. The programs aren't any smaller than they were before. And one of the hallmarks of object-oriented programming, if you have any sense of whether you're doing it right or not, is that the programs are remarkably smaller. Because there's a way of using the design that is not simply imitating a bad old idea, which is data structures, and trying to shore it up by putting it in an orthotic brace, but in fact to go beyond the notion of data structure. So for instance, in an Ada way of doing object-oriented programming, one typically comes out with something that looks very much like a data structure. It has fields that are to be written to. It has fields that data is to be taken out of. The structure is static. There's no actual process going on, and it's essentially a slightly more abstract way of doing data. Typically in an object, a good object will not actually permit you to write assignment statements to it at all. Because an object generally will not look at all like a data structure. Just to give you an example, we can contrast a personnel record as it might be done in Ada, in which we still wind up with fields as we had them before. Some of the fields might be a little bit more connected, but it's still a large thing. It's still passed around as a passive object. We can contrast that with an object-oriented approach, which would be to try and turn the personnel record into something much more like a real person. In other words, this personnel record, instead of sitting there on a file waiting to be manipulated, would actually be trying to participate actively in some sort of simulation. Instead of changing the person's age from the outside, the way you might do in a data record, the age of the person would change dynamically as the birthday was passed, because there was something in this object that was actively looking at the clock, actively running in some sense. The notion of being able to edit the object from the outside would be much less in the sense of editing the actual fields. So objects, even in a programming language in which everything is an object, like Smalltalk, objects tend to be larger things than data structures. They tend to be components, active machines that fit together with other active machines to make a new kind of structure. Just to give you an example of a modern attempt at large-scale object-oriented programming, which hasn't been done very much. For a long time, the largest object-oriented system was Smalltalk's own system, which was, even though it had its own user interface and its own operating system and its own sets of editors and facilities and file system and every other kind of thing, the Smalltalk 80 system that is distributed by Park Place Systems, for instance, is only about 40,000 lines of code, which to me is approximately 4 to 10 times as large as it actually needs to be. It's actually kind of junky in various ways. But when you consider that the Unix kernel alone is 400,000 lines of C, and that is thought to be a rather small kernel in the operating system domain, you can see that most object-oriented programming, historically, the programs have been tiny. All of the stuff that we did at Park that led to the Macintosh could be summed up, and this includes the equivalent of about 15 different Macintosh applications, including Mac Draw and Mac Paint, and all of those things were summed up by approximately 175 pages of code, or approximately 8,000 lines of code. That included the operating system, the user interface, and everything. These programs are tiny when they're done right. Because of that, people have been very suspicious of them in the world, for instance, that you come from. You know, does this idea really scale? Is it just for toy problems and so forth? The most recent example of object-oriented programming in the large that I know is one done by Arthur Andersen Consulting at the Brooklyn Union Gas Company over the last year. Now, Arthur Andersen, I don't know how large the jobs typically are at McDonnell Douglas, but Arthur Andersen Consulting typically, and I think they do some work for McDonnell Douglas, but typically when they get to work on a job, their clients have already failed a couple of times in implementing it. They're usually called in at the last moment. They charge $20 to $50 million a pop for one of these jobs, and their jobs typically run to about 1.5 million to 2 million lines of COBOL. This is done over a period of about 1.5 years to 2 years by a highly trained group of people I think of as technological Marines. They have a very rigorous, high-spirited training facility called St. Charles. They have approximately 27,000 people who do this kind of work, and it's a fascinating setup. I'm on their technical advisory board, and I got on the board partly just because I was interested in the culture of this particular company. I was really surprised that, given how successful they've been, that they have been shifting their entire set of operations over to objects over the last 5 years or so. It's an enormous change for them because they have, it's not the change in going from a non-object-oriented language to an object-oriented language, it's the change of going from one kind of culture to another kind of culture. And it's a change that, as Kuhn mentioned about paradigms, the reason that paradigm shifts take 25 years or more in science is in order to have a paradigm shift in science, you generally have to let the old physicists die off. Once people have learned a technique and have gotten comfortable with it, it's extremely difficult for them to go to something else. The Macintosh user interface in its early stages had that difficult. People had gotten so good with function keys that they actually felt diminished by using the mouse, even after it was shown to them that the mouse is 4 times more efficient in speed over what they've been doing with the function keys. It didn't seem that way to them because they'd gotten so adroit with it. And the same thing is true with any technique that people use. So Arthur Andersen has done a number of different pilot projects, but last year they started the first large implementation. This is a project that was a re-implementation of a system that had been done some years ago. And it was originally designed to be done in the standard Arthur Andersen case tools. And the estimate was 1.7 million lines of COBOL and approximately 2 to 2.5 years of implementation time to do this enormous system, which is both an accounting system and a management information system. And as an experiment, they decided to let the New York group, which had been the pioneers in object-oriented programming, do an implementation using object-oriented techniques. Now, of course, they didn't have an object-oriented language to work with for their end result. This was to be done on IBM mainframes, 3090s. There are no object-oriented languages extant on the 3090. So they did a trial implementation to test out the design in Smalltalk, taking a few months to do it, and then wrote a set of library routines and some pre-processing macros for PL1, and then re-implemented this project with about 10 programmers in PL1. So the results of that are now in. The minor interesting thing was that they got done about 6 months early. The major interesting thing was that the amount of code that actually had to be written to do this amounted to 150,000 lines of this libraryized PL1, as opposed to the 1.7 million lines of COBOL that their estimates had done before. So this is a factor of 11 less code. And from their standpoint, the 6 months was down in the noise, because the months that they're interested in are the 5 or 6 years of maintaining the code from then on and being able to reuse those modules as they're going to be able to on other 3090 implementation. So in some sense, the fact that you can program faster, that you can save time and so forth in object-oriented programming in the larger world is not nearly as interesting as it is in research. In research, basically the ability to do quick prototyping dominates almost everything else. In the large world, the world that you come from, the world that Arthur Andersen is in, quick prototyping is something they'd like to do. They're starting to do it, but it's not nearly as important as maintainability. Reusability is the second thing. If they can reuse a module as a component in some other system, then they have saved themselves an enormous amount, not of time, although they have certainly done that, but to them it's not time, but it's designer skills. The thing that all large companies are weak on is having enough designers to go around. There are usually plenty of people to write code, but the designers are few and far between, and this notion that a successful design can actually be moved from one place to another in components is something that literally drives the Arthur Andersen people crazy with joy to think about. So they have now come up with an object-oriented repository and are starting to craft rather large, useful objects that can be used as standard components and building blocks in various systems. And we'll talk a little bit later about how one goes about. To me, this is what object-oriented programming is about. It's not saving data structures from itself. It's not making a slightly fancier data structure. It's not even making a data structure that can implement certain kinds of constraints within itself and so forth. It's thinking of those objects as independent machines, going back to this whole biological notion that it's one thing to build cells and it's another thing to build tissues. And for people who are just starting out in object-oriented programming, they're usually thrilled that they can build cells. But the real goal is to be had when you move from cells to thinking about what are the tissues, what are the conglomerations of these atomic-style objects into components that if you were to have 300 or 400 of them in a repository usable by any programmer, what would you be able to build? Could you be able to tinker toy things together? Could end-user programmers be able to do a considerable amount of the programming and retailoring of things and so forth? So the real change, if there is one, I think it's coming faster than we think, that object-oriented programming is going to bring along, is actually both a change in the way professional programmers do their work, but even more so a change in the way these applications are designed. Another example, for instance, at Apple, now we design all of the applications that we do as though they are going to be actually tailored, not completed, but tailored by an end user, a person who has programmed almost not at all, a person who's used HyperCard a few times. So this is a really big change, and it's something that has been talked about for 20 years or more, but it's something that just now is possible to actually do. What does it mean? Well, it means what you like when you get an application from somebody is to be able to use it right out of the box, read the manual, understand what it is, don't have to sit down and think about it as a kit or anything, but just use it the way you're used to using it now. It's a temporary solution to some set of problems you have right now, or else you wouldn't be using it. But a month later, your whole attitude about this application has changed completely. A month later, now you're saying, boy, I wish this thing could do this, and I wish this thing could do this. Everybody does that. A person who's never programmed before, who's only used a computer for a couple of weeks, after a couple of weeks they'll say, boy, I wish this thing could do this, and I wish it could do that. And that's the point where you'd like to hit the hood latch button on the application and open it up and see something in there that was comprehensible. Right now, if you open an application on the Macintosh, you open it up sort of like looking into the hood of a Mercedes-Benz or something. There's this mass of tubing, and if the thing had a carburetor, you couldn't find it because it's a mass of spaghetti, mostly machine code on desktop micros, but it doesn't matter whether it's machine code or Fortran, it's a mess. And on the other hand, what the user wants to see when they open it up is something that looks like a Model T. They want to see a schematic. Even if there's a Ferrari underneath the Model T, they want to see a Model T. They want to see a schematic engine of what makes that application tick, because they've already got an intuitive notion about how that works. And then they would like to be able to make changes at the level of that schematic engine. There are a bunch of applications you can buy for the Macintosh now in which that's possible. An example is Focal Point, and many other applications written in HyperCard, because HyperCard is an object-oriented language set up so that professional applications programmers can give you not just architectures, not just a kit, but working architectures, working kits, and then after you've used them for several months, you can make the change. That's going to change the whole way we go about designing things. Professional programmers won't be designing programs for each other, or at its worst, professional programmers tend to design programs that will keep them in job security. There's a class of programmer who delights in the obscure. They love the fact that they are the only ones that can understand how this program works. And there's a maxim that says if you're the only one who understands how it works, you don't understand how it works. And so progress isn't to be made there. So I think I'm going to go into give you an idea about where some of these ideas came from. The one thing I think you'll maybe a little bit surprised at is some of the earliest object-oriented ideas were some of the most sophisticated, and that we'll be revisiting them in the next 5 and 10 years to come. One of the reasons for this is that because you couldn't make money in computing in the 60s, many of the people who had ideas about how computing should be done in the 60s had extremely pure conceptions. Those conceptions are powerful yet today, and it's worthwhile showing you a few of them. So just as a reference point, always like to start off with this slide because this is my vote for the world's first personal computer. This picture was taken at Lincoln Labs in 1962, summer of 1962, and this is a machine called the Link. And it's especially appropriate to mention here since the person who invented this machine, Wes Clark, had a research project at Washington University for many years. Sponsored by ARPA, those things that look like deck tapes over on the side, he actually invented. They were called link tapes originally. And this is kind of a metaphor for our talk, which is the best that DEC could do with these ideas. DEC came out of Lincoln Labs as well. When DEC saw this machine in the early 60s, it said, boy, what a great way of making a small mainframe. And it immediately adapted the architecture of the Link to make mini computers. But DEC said, well, people aren't used to looking at displays. Let's make that an option. So they took the display away. And people didn't understand what was actually on the link tapes, some obscure stuff. So they said, well, let's put files on the link tapes. We'll call them DEC tapes. And out of this machine, DEC was able to come up with the astounding idea of the mini computer, whereas in fact, about 2,000 of these were built in the 60s, and an astounding, as far as I've been able to determine, an astounding 900 of them seem to be still working today. Now, they were designed for biomedical labs, for technicians who needed to do their own programming and needed to do real-time experiments, and it was an almost perfect machine. By the way, what was on those original link tapes, what was on there were the pages of the virtual memory this first personal computer had. It's very hard to go out today and buy a personal computer that has a real virtual memory. This machine had it back in 1962. So it was an excellent idea, but like many things thought up, it actually was so far ahead of its time that it took another decade or so for people to catch up to it. One of the very first object-oriented software systems, and one that's, I think, of particular note to us in this talk, is Ivan Sutherland's Sketchpad, which was also done at Lincoln Labs on the TX2 computer, which was the last computer in America large enough to have its own roof. It, in fact, was about 4 times the size of this room. And every Thursday, they would take it down and change about 10% of it, because they were always putting new things. It had some of the earliest core memory ever devised, and it's quite a remarkable machine for its day. It was used as a single-user machine by Ivan Sutherland to invent Sketchpad. And you see him here. He's working with a bridge truss. Sketchpad is very difficult to appreciate just by looking at slides, so I thought I would show you a videotape of it in operation. So if we could run the first videotape. take a look and see what. This again is the summer of '62. This is tape number 1.
Hospital. They're talking high tech. 45
Stop that for a second.
As a phasing.
Stop. Could you, I thought that was rewound. Could you rewind that, please? And then show it. Now back then they didn't really have computer displays as we know them today, so the TX2 here is actually simulating the lines by drawing dots. Rubber band technique that you've seen before. Now here's something that Ivan invented, which is he's pointing at the edges and telling Sketchpad he wants them all to be mutually perpendicular, and Sketchpad just solved that problem. We see that Sketchpad is the first system to have a window. The virtual paper he's drawing on is about 1/3 of a mile on a side. Here the constraint was make the lines parallel. Now the constraint is collinearity. So Sketchpad wasn't just the first graphic system, it was also the first non-procedural programming system. So everything is controlled by non-procedurally giving goals that the system has to figure out. Here he's making the guidelines invisible to get some dashed lines. So he's made himself a flange. Now he wants to make a rivet. And this is why it was called Sketchpad, that you didn't want to have to be precise. You wanted to be able to just sort of sketch things. He's going to use that as the center for an arc. And now he's going to, again, point to those and say, make them mutually perpendicular. That pulls the center, which pulls the arc, which makes it symmetric, which makes a rivet. And because of the way the program is implemented, you can actually see it solve the problem. It's actually quite sophisticated. This is a nonlinear problem it's actually solving. So no matter how he distorts it, it comes up with the same general shape, and he could constrain the ratios of the lengths if he wanted to. Now what he's been working on there is actually what we today would call a class. He called it a master, and this is an instance of that rivet. You can make it larger or smaller. So he wants to latch it into the flange here. You can see that this program rapidly led to better display designs. These are other instances of the rivet. And now he goes back to the master and says, well, let's make those guidelines invisible so it looks more like a rivet. And we see that the instances dynamically feel that change. So these are not copies, but actually dynamic instances. Okay, and now he shows that any constructed thing can be a master. So he had made the flange with a rivet into a master, and now he's pulling instances from it and rotating them and changing them and so forth. Okay, if you stop that tape, please. So Sketchpad, even today, is an amazing program. You can't buy a graphics system that is nearly as good today in the sense of it being a comprehensive system for allowing you to set up problems, allowing you to solve problems. Its implementation, not just its appearance, was also object-oriented. And this style was something that Ivan Sutherland came up pretty much on his own because of the difficulty in dealing with many different kinds of objects and having them solve constraints and be able to make pictures for them of themselves and so forth. So he got interested in this idea that each object could actually have its own drawing procedure embedded in it, and all he had to do was be able to send the message draw to any of the objects, and it would invoke the correct procedure, although it would be a different procedure each time. And the same notions were later used for constraints. Now, I once asked Ivan, I said, Ivan, how is it possible for you to, in 1 year, just by yourself, come up with the world's first graphics system, the first non-procedural programming system, and the first object-oriented software system? And he said to me, well, I didn't know it was hard. Fortunately, it didn't. And actually, it has barely been improved on since. There have been some improvements since a system called ThingLab done at Park about a decade ago or so was an improvement on it. This whole area of constraint-driven object-oriented programming is something that is a hot topic in research right now. And I think for the first time in 20 years is actually going to yield some fruit over the next 5 to 10 years. The reason is that people who do mechanical design, particularly such as you do here at McDonnell Douglas, require now, for the first time, serious simulation of the mechanical design, particularly how it articulates with other parts of the design. Really want to have a simulation job shop built into the design system so you can do a lot more than just finite element analysis, but be able to do analysis of linkages and other kinds of situations that are too difficult to do simple analytic solutions or do finite element analysis of. And the answer to this is a kind of constraint-driven, object-oriented design that Sketchpad actually invented the first kind of. So let me give you another example. I'm going to go to the number 4 tape this time. No?
You can hold on just for a couple minutes. Since we are videotaping this, we do need to change tape about every hour. So those who didn't have a chance to come today will
Okay.
get the whole
Okay.
seminar on tape. So let's
I'll pause.
3 to 5 minutes.
Well, had some interesting questions. Actually, one of the things I should have mentioned at the beginning is I'm perfectly happy to entertain questions at any point. I believe that I think we have an hour and a half, that at least an hour of the hour and a half, I think we should spend talking about issues that concern all of us about object-oriented programming. I have some of my own. People who are starting out on it may have some trepidation. They may wonder where it's going, what the actual leverage is. I had a question asked again about the difference between abstract data structures and what I think of as a real object-oriented style. Another question was asked about, is there any way of preserving already written COBOL and Fortran code in an object-oriented fashion, so it doesn't all have to be thrown away. And maybe that last question is one that's worthwhile answering now. A lot of companies are trying to figure out what to do about object-oriented programming, particularly given that there don't exist any good object-oriented programming languages for programming in the large. Smalltalk is not a good language for programming in the large as it's currently distributed. It's a great language for learning about object-oriented programming because it's written entirely in itself. And so you can learn how an operating system, how a user interface, how applications, how little things and larger things can be represented in an object-oriented form, how inheritance, subclassing, and so forth, all those things, Smalltalk is ideal. Of the Smalltalks around to look at, the one that has the best manual is the one called Smalltalk V, and it runs on both the IBM PC and the Macintosh. It's not it's a rather complete system in a number of ways. The other system is called Park Place Smalltalk, Smalltalk 80, and it is sort of the granddaddy of the Smalltalks that Xerox has released. It has a even more complete set of system tools and some very ambitious applications written in it. Both of those are worthwhile looking at. But for programming in the large, objects aren't enough, I don't believe. And the reason is that at some point, it's not simply a matter of piecing together something that is supposed to run. It's a matter of being able to verify different sections, different parts, different modules independently to be able to unplug and replug. And even, I think, in many cases, it's desirable to allow different implementation languages to actually be used. Now, if we look at the standard so we have a glob, and the main principle in object-oriented programming is to separate the outside from the inside. So on the outside, we have a variety of messages that we're willing to respond to. And on the inside, we have some methods. Oh, sorry. We have some methods that may or may not correspond to these things on the outside. Because remember, the idea is we're not supposed to understand what the inside looks at from looking at on the outside. An outside thing might even correspond to a little data structure inside. A thing equally innocent might correspond to an enormous amount of code. There might be code in here not directly connected to this. And in fact, some of the messages that the object may be able to receive aren't directly characterized in terms of some outside protocol. Lots of different variations here. But the most important one here is that we're trying to separate a protocol from some methods. At this level, and then if we think about going a little bit more fine-grained, where we start having zillions of objects interacting, in a sea of messages, and in fact, some of the objects might not even be on the same machine. They might actually be over here. A good object-oriented system, you shouldn't be able to tell what machine you're running on. So that's what messages are all about. Very quickly, when we're starting to build a large system down here, we've got something interesting. We have absolute protection, but we still have confusion, right? Because you can have thousands of diamonds that are impervious to all normal wear and tear and still not be able to build the simplest structure out of them. They may be too shiny, may not be able to pile them up. They may not fit together, but by God, they're perfect. So what I'm trying to say is that the protection issue is a critical one, but it still doesn't guarantee that you actually have an architecture. Now, in Smalltalk, in most object-oriented systems, how you come up with these guys is governed very much by convention. There's a particular way, like it's a convention in Smalltalk systems that one of these guys will always be called print. So that for every object in the system, you're guaranteed that one of the messages you can send to it is print. And theoretically, what that means is this little patch of green in here that corresponds to print is supposed to print for you. Now, there's nothing in Smalltalk or any other object-oriented system right now that guarantees that printing is going to be done. In other words, it's strictly conventional. It's something that everybody agrees to. It's like overloading operators in Ada. When you overload plus, in order to give plus more meanings for different structures, you're usually trying to adhere to something metaphorically similar to what plus originally stood for. So for instance, if you have a plus that adds two numbers together, you might overload it to apply to arrays so that the operation is some sort of point-by-point addition, maybe vector addition. Sometimes you might overload strings to what could plus mean in strings? Well, one of the ways of thinking about strings algebraically is that plus means concatenation because it's a way of adding two unary numbers together and so forth. And at some point you start stretching it as you stretch the metaphor. But generally you don't want plus to go off and do some sort of multiply or something else. But the only thing that controls that is some agreed on set of conventions. And because of that, what this protocol is, how complicated it gets, and so forth, is the most important part in any kind of object-oriented design, but it's also the most fragile. The fact that there's nothing to protect print is absolutely critical. Let me give you an example of what we could do to protect print. One of the things we could do is to have, instead of having print just be code, we could actually have a print class and its offspring, its instances, are actually structures that look like this. Okay, in other words, each offspring of print is a message method pair in which unrestricted code writing over here is not allowed. Does everybody understand why this is an interesting idea? Because if you can write anything here, then JRandom programmer often will as you go along. And the fact that the system seems to be conventionalized at this protocol message level which is the very charm of object-oriented programming, why object-oriented programs work so well and why they fit together, gets destroyed as the amount of generic information in the actual methods gets diluted. But if another way of doing an object-oriented system is to actually make classes for each of the major code types that you're going to write. And what you get here is something that would insert itself in here, but in fact the only code you're allowed to write are certain little restricted boxes in here, and this thing guarantees that it's going to print for you. It's not going to go off in 0 byte 5 of some system file. This thing, because it came from a print class and because the print class does printing type things, every piece of code that goes into a protocol actually is going to do something like printing. And what you're allowed now is a certain amount of parameterization, a certain amount of freedom, but the meaning of print now has been nailed down because there's some actual code from the print class sticking behind here that you can't see that's going to make every effort to deliver a result that is what you want. Now, this is like types in typed languages, except it's stronger because it controls the goal of the result. The goal of the result, not just the shape of the result. Right? In a typed language, when you have a typed variable or a typed procedure, what you can state is that I have some integer parameters and I'm going to deliver a floating point result. What you can't say in the type statement is what the intent of that procedure was. The only intent that you can indicate is it's going to give you some sort of floating point result. You can't say it was supposed to give you sine or cosine or anything else. That is up to the convention of the actual programmer itself. So what I'm just pointing out here is that if you take a system in which there is a protocol, you can get a lot out of it just by having the protocol be a convention agreed on by everybody. As you go into a larger and larger system, that inside-outsideness will protect against the inside getting dissolved by some hostile action by the outside. But what will get diluted as you go to a larger and larger system with more and more programmers is whether the protocol is going to have any meaning. Practical example, in Smalltalk has approximately, Park Place Smalltalk has approximately 5,000 of these green things. Each one of them is there, and each one of them can be reused by inheriting it from somebody else. The number of red things it has is on the order of 2,100. That means that the amount of how generic the code is with respect to the protocol is not much. Right? The number should be more like 400 or so different red things, 400 concepts, and say 5,000 realizations of those concepts. Now, print is the happy exception to that, because if you have 154 different kinds of objects, then there are 154 different green guys, and only one print concept. So this is the same technique that people use overloading of operators for. You want to reduce the concept space by making it more algebraic. Take a concept, make it as metaphorical as you possibly can, and like equal is a good one. What does equal mean? Some systems it means I'm looking at exactly the same thing. Some systems it's okay for if the same things look the same. Some systems is if under some particular evaluation rule they evaluate to the same thing, or they might evaluate to the same thing. So equal is one of these very slippery notions, because it very quickly becomes useful to think of equal as being very useful in terms of equivalent. This is equivalent to that. That's a generic notion. So again, you might imagine that one of the things you might like to have be generic are comparisons. Equal. Equal is a much stronger one, of course, than greater than or less than, because greater than and less than involve some sort of sorting. But again, greater than and less than don't have to apply just to numbers. In Smalltalk, there's a superclass called magnitudes. And anything that can be sorted in any way under any kind of sorting rule is underneath magnitudes. And underneath magnitudes are things like less than and greater than. So for instance, dates are an example, times, time intervals. Anything that can be sorted in any form, you can those what you would call operators in Ada are automatically overloaded. Now, what happens in an object-oriented system is you always start off with a nice set of these, and then as practical programmers chew on it, the heat of debugging, one of the things that we discovered is that even good programmers don't make up generic operators for things. What they do is they make up any old word that they can think of at the moment, write a method for it, and continue on. The result is that what the object-oriented style was buying for you starts diluting, starts gradually diluting away. The manuals get larger, and all of a sudden you're back to something that is close to what you had before. So I'm not sure if people didn't understand this explanation. I'll be glad to go over it again, because it's one of the important examples of something that you can actually do with an object-oriented system. Everybody more or less get what I was talking about, that you can actually legislate. One of the things you can do in an object-oriented system is to legislate to some extent even what the code that the programmer is going to write is going to deliver to you. You can build in to these main concept classes the tests to see whether the code is at all behaving the way you think it is. Those tests can be run independently of the programmers who are writing the code. Now, another thing you can do using these protocol ideas is, horrible as it sounds, there's no reason why you can't put some COBOL in here. This is not something that people do in a typical object-oriented language like Smalltalk, because it's designed to write all of the methods in itself. But if you think about this whole notion here as a binding mechanism for a component, not just as a way of protecting a data structure, but a binding mechanism as a component, then what you really are programming in terms with is the blue and the red. What the green is almost completely independent as long as it conforms to whatever this guy wants it to be able to do. And what I advise large companies when they are embarking on object-oriented programming is to do a few systems using something like Smalltalk, or preferably, just to get an idea of what it's about. But then think of all the things that you've already learned about controlling modules and systems, and realize that the small sizes of the code of the Smalltalks from the 70s don't have all the protections in there that you actually need. What you really need is what these days is called a configuration language, a C language, configuration language. And this language can be independent of all of your method languages. It's something that is dealt with at the operating system level. It's something at which the protocols are chosen as much as possible ahead of time. It's a standard vocabulary of concepts that you're going to use to write in. It's one in which the protocols are controlled by active code that give you places to write code and insert other code that allow you to bring over a COBOL routine or a Fortran routine or whatever the heck you want and bind it in. It's a binding mechanism. It's a way of setting up environments for debugging modules independently of each other. It's a way of assuring yourself that a module will be able to move from one place to another. It's a way of discovering whether you want to use a module. So at some point, the ability for a human to read this configuration language is going to be much more important than the ability to write it. One of the embarrassments that you often find in an object-oriented language is you have all this reusable code, and it is too hard to find the modules you want to reuse. Smalltalk has a lot of that flavor. Anybody who's ever tried programming, especially in Smalltalk 80, is bewildered by the fact that the system is completely written in itself. There are tons of usable things in there, and yet it is such a pain to find those things. You wind up tantamount having to read other people's code, and then in order to find out whether you actually want to use the stuff. So for instance, what Arthur Anderson is doing right now is to try and come up with something that is completely independent, just completely X out, forget about the interior stuff, just come up with something that is basically modules in terms of blues and reds, making the red message protocol be as powerful as possible, controlled by other things, and then using that as a dynamic binding mechanism for configuring programs. It allows them to take large sections of database and SQL calls that they've already done and bind it into an object-oriented framework as an example. Yeah.
Could you give an example of a configuration language?
Yeah. So configuration, let's start off with the things that you might want to have in it. Now, there's only, I only know of one actually good configuration language that's been done. It's a language called C Mesa, which was done by the Park Computer Science Lab about 10 years ago. And it served exactly this purpose. And here are some of the things can have it. There's some things that you'd expect just from your previous experience. You'd expect that there would be some sort of message name for something. You'd expect that there would be I/O parameters, so that you would have input expectations, output expectation, a good configuration language has an executable predicate, which you can think of as a goal, that it may have a variety of them. And I connect those with, when I say input expectations, I mean not just the types of the parameters that you expect to send to it and the types of the results, but also these predicates. Predicates, you can think of preconditions on the input side and goals on the output side. You can think of those as being executable. There are environmental expectations. One of the difficulties in most object-oriented programming languages is, although you can protect an object, what you don't have any sense of when you want to move an object is what the object itself expects to have as environment. Give you an example, in Smalltalk, you can write an object move it from one place of a particular Smalltalk system to another. But when you want to take it out of your Smalltalk system and give it to somebody else's Smalltalk system, you often are unpleasantly surprised. And it's not that the object has been sullied in any way. It's that it has some other assumptions about its environment that you weren't thinking about before. In particular, Smalltalk allows you to do the somewhat obscene thing of allowing you to go and change existing superclasses to make them more the way you like. The benefit of this is that every class in the system feels this improvement. And the problem with it is if that improvement is important, then you've all of a sudden have done away with your portability. So what I'm trying to point out here is that the modularity you get in object-oriented programming is slippery, and one of the most critical things to do is to be able to pin down the amount of modularity that's actually there. I'm going to go into that in a little more detail. So there are more things that are here. People have designed configuration languages in such a form that you can actually, from the runnable parts of the stuff, that you can actually derive an explanation mechanically of what the method and what the module itself is supposed to do. Okay, so there are any number of things. But basically, it's something a little bit more closer in spirit to Parnas, Dave Parnas, who did one of the original notions about information hiding, although it wasn't object-oriented, than what you might think of as straight object-oriented doctrine. And that each one of these things is part of this blue notion, and that this forms a class from which we get the various instances that our system is actually made up of. So each little instance now, it is often the case that if these two predicates here are done correctly, you can actually you do your prototyping by running the blue thing essentially without any green things inside of it. Or you can think of there being just tiny little green things that come along because of what these are. Yes? Okay, it's similar to Ada, except that Ada, for instance, doesn't have inheritance. And so, does everybody here understand what I didn't come to give a tutorial, so I'm not sure what I'm supposed to assume everybody knows about the thing. But in most object-oriented languages, there's this notion of inheritance, that you can define something very general and abstract, like, say, a thing called a magnitude, and a magnitude, maybe something even more let me use a fresh sheet of paper. Start off with something really abstract, like a general object, and then one of the operations that an object you might want to have for every object is equality. Then a little less abstract, you might have something called a magnitude. One of its operations might be less than. But there still might not be any notion of what addition is. Coming down a little bit further, you might have something called a number, and it might have a notion of plus, and there might be various specializations of numbers. So you might have an integer, a fraction. These guys might have their own versions of plus. And the notion of inheritance is that very often you can get a compact description of a wide variety of behaviors by factoring out behavior as abstractly as you possibly can. You move it as high as you possibly can. And occasionally you may have to give your own versions of things, like an integer may want its own version of what plus generally is. It may even want to have its own version of what less than is, or it may be able to use this general one up here. But inheritance actually allows you to cascade descriptions, and in a number of object-oriented systems, particularly the AI ones, you can actually blend them together in various ways. So you can actually say this thing is not just a number, it is also a geometric object, and inherit a bunch of things from the side as well. So when I talk about doing the configuration stuff, I mean to imply all of the things that you usually do in a typed language, but also applied to a system that has inheritance. Because its inheritance in object-oriented languages is how you share things. The goal of, or at least it has been the goal for the last 20 years of people who do this and write very small, very reusable, very compact code, the goal is to make the things that are shared as abstract and inheritable as they possibly can be. So you want the smallest number of maximally independent concepts that you can tinker-toy together and have some confidence that the act of tinker-toying is going to give you something that also still works. The whole idea in object-oriented style is to linearly combine things together. Now, an ADA package allows you to subsume some of the details of a data structure. It does not allow you, for instance, to define generic operations which are then inherited by subclasses, because it simply doesn't allow you to subclass. And what that leaves you at is a single layer of description for something which you can get instances from, but you generally in ADA do not write an abstract thing that you're going to get instances from, because usually these very abstract types like magnitude and so forth aren't things that you want to use directly. They're really placeholders for general code and strategies. And this is a foreign idea in the ADA programming world, which is almost entirely concrete. Yes?
Don't the ADA generics still support that a little bit?
Well, they do actually, ADA shouldn't even really call them generics. But it's, it's okay. Anybody can use a name for whatever they want. But that's a different way of thinking about what generic is than what I'm thinking about here. The generic power in an object-oriented programming language is your ability to not just reuse a concept sideways, but also to advance it abstractly. The more you can advance it abstractly, the more chance it has of being involved in an abstract design, the less probability you have of having to recode. Whole strategy here is to avoid recoding. Remember, we got off on this thing of just pointing out, it was just really just an aside remark, that you can make a very strong object-oriented programming language by being completely independent of whatever the methods are actually coded in. That was the whole point behind that digression. That as you build yourself object-oriented tools, you're much better off worrying about the integrity of the individual objects, and then the next thing is, can an object be a component and fit into some larger scale protocol? When I say component, I mean something like, let's say, a paragraph of text or a generic gear, something that actually has a fair amount of meaning behind it. It might even have its own inference engine as part of it. Talking about something that can be used in a wide variety of cases in which the sharing is more than parametric. You're really getting not just a class of things, you're sharing a notion that somebody has come up, a concept, a set of concepts that somebody has come up with. Is this obscure? It's the hardest, it's actually the hardest thing to explain, simply because I'm going to try another pass at it. One of the reasons that it's hard to explain is that this notion, because of Ada being called object-oriented, being taught in school as being object-oriented, actually has clouded the issue considerably. So it's very difficult to even explain why some of these ideas are more complex. Let me give you another completely different idea. And this has to do with another way of thinking about modularity. Now, in most object-oriented systems, the modularity that is gotten by them is one that is regard to the state that you put in each object. What isn't modular is the control. This is another set of issues to talk about. So, for example, one of the things that you may see when you're looking into an object-oriented programming is you may see the state neatly encapsulated, but you may see control going all over the place. What happens when you send a message? The answer is often, I don't know. Goes here, goes there, it finds somebody here, talks to this guy. Dozens of things happen, and I can't even tell whether control is ever going to get back to me. That's often the state of affairs. Now, what would happen if we actually made control modular? We'd have something more like this, where instead of control going through the objects themselves are sitting in a sea of messages, but they don't actually originate them themselves. Now, how is that possible? Well, one way you can imagine for it to be possible is for the objects to simply say, I need to know the following. Put needs in here. Now, there are object-oriented systems. One of the ones we just developed at Apple and one that we did at MIT is an object-oriented system in which you never send a message. Okay? You only receive. How is that possible? Well, the system contrives to make the messages get to you by looking at your needs and looking around to see who might supply those needs. Okay, is this obscure? Okay. So an example is, suppose you're a button whose job it is to move the corner of a window. So one of the ways of programming that is for you to be in a loop, constantly looking to see if the mouse is coming into you. Okay, it's a polling solution to the problem, or somebody is polling somewhere but you're constantly looking to see whether the mouse is coming in. When the mouse comes in, then you say, okay, now I know what to do. I'm going to latch onto the mouse's coordinates, and I'm going to tell my window owner exactly how he should be moved around. And so as we move around the corner, the window corner moves around itself. And so that's this kind of style of programming. Control is explicit. We have to poll to find out things that are going on. The other way of doing it is I could just say, I need to know when the mouse comes into me, and then I can do my job. This is like an on condition. But it's an on condition that has to be scoped, because we can't have it happening every time, for instance, the mouse button goes down. But we can imagine that this guy can say, okay, I have a set of conditions. I'm not going to explicitly look for it. I'm just going to tell the world that if I had these conditions come true for me, then I would be able to fulfill my obligations to the rest of the system. I'd know what to do. Likewise, the window that encloses this guy could also have a set of conditions that say, well, if my corner guy starts moving, I should probably move too. I'll change my size if he moves. So if only somebody would let me know that, then I'll go along. See what this is like? This is like constraint programming. Okay, we're going from a procedural style in which control is passed explicitly around to a declarative style in which we're simply indicating needs, and the system, without having to do any problem solving, is picking up the slack by providing the actual information in the forms of messages. HyperCard has this about halfway. It's a technique we've been experimenting with at Apple for the last couple of years. And what it looks like it's able to do is to completely remove the necessity for actually being able to follow a control flow. What does this mean when you move an object from one place to another? Well, when you move an object from some place into this kind of situation, nothing is going to happen. Whoop, sorry. It's kind of a tiny screen, isn't it? When you move a new object in here, in this kind of situation, nothing is going to happen to that object unless you go in and recode somebody else in order to send it some messages. Right? And so my modularity of being able to move an object from one place to another depends on me being able to do some kind of modification on the system that's already there. That's not so good. It's good in the sense that this object is guaranteed not to hurt anybody, and it's going to protect its own self from being moved around. But in fact, I still have to go in and make some sort of modification in order to get control to flow. When I put in a new blue guy here, and he has all his needs specified, is he going to be able to run? Why? Because he doesn't have, because the whole idea is that he's not intertwined with anybody else's control. He simply is saying, I know what I need, God damn it. And then the question is can the system actually deliver those needs just because he's a new thing? And the answer seems to be yes. This is a peek into the object-oriented programming of the next couple of years. Now, interestingly enough, the need to do things this way came out of yet another project with children. All of the object-oriented stuff that was developed at PARC and the Macintosh user interface came from a set of designs to try and allow children to do serious programming on a computer. That was what forced object-oriented programming out into the open. The last set of stuff that we've been doing with children at Apple forced this out of the open because we wanted children younger than 9 to be able to program. And children younger than 9 have a very hard time following control flow. And of course, when we were thinking about that, we were thinking, well, of course they have a hard time following control flow. So do we. Except we're used, see, the problem is adults are used to suffering. So that's why I like to design for children. So designing this new programming language for children, I'm going to give you a little example of some of the stuff programmed in it. This notion of making control completely modular by going to a needs thing became apparent. Yes?
Everything on that slide seems relatively mechanical except one.
Yeah.
That is the thing, whatever that is, that generates that sea of commands.
Yeah. Well, it's complicated because I'll give you a simple example, and then maybe we can generalize it a little bit. The motivation came from a couple of years ago of wondering why it was so easy to program in spreadsheets, and wondering what spreadsheets would be like if they were more object-oriented. Because I've always thought of the spreadsheet cells as being almost an object. And spreadsheet cells have this nice characteristic that they are these, aren't they? In other words, the very act of writing the spreadsheet expression indicates to the rest of the spreadsheet system what your needs are. Now, usually they're pretty simple needs. They're just, I need to know the values of so-and-so cells relative to where I am. But I got interested in generalizing that and started off with a spreadsheet system that I did in Smalltalk that had a spreadsheet optimizer that first started off simply trying to look at places you wanted to get values from and building a propagation network rather than executing every cell for every change in the spreadsheet. I think most of you are aware that most spreadsheets today do not execute every cell. There's a propagation network built by the spreadsheet compiler that you don't see that tries to find you the minimal number of things that have to be executed every time a change is made in the spreadsheet. I started working on that. And then the next thing is to go to Booleans, where you're interested in whenever something, like for instance, whenever this is equal to that, I would like to do something. Or whenever this is less than that, I would like to do something. And I'll just give you a hint of it. So you start out with this fairly simple idea that if you have a variable somewhere, one of the things that you can do is to link, you can have a link to all of the different places that ever need the value of that variable. And when this changes, you simply fire off all of these guys, and you get the desired result. Let's take an expression now. So if we take an expression like A is less than B, or C is greater than equal to D, and then ask what we'd have to do to that to make that efficient, the answer is you make this thing into a little tree, and at each stage, each node of the tree, you hold the value of the thing so far. So in this case, the A value would be linked through here, and you can think of the tree as pointing upwards. Okay, and we can presume that this, let's make this and just for the heck of it.
assume that this is false, and we assume that this is true and that this is false. Let's do it the other way. Make this true, this false. So the idea is now, if A changes, the insight here is that all you have to do is compare it to whatever the current value of B is. Let's say this goes to true. You don't have to recompute this guy because it didn't change. It's already part of this frozen result. And then you come up and recompute this guy. So what you basically have done in this technique is to have sorted the actual computation that you have to make. This way of doing things is called a continuously evaluating expression. So it's a conglomerate of things. It's actually a little computation engine designed to compute in parallel, and only the stuff that needs to get computed gets computed. So the computation now, the compiler, instead of compiling machine code in a system like this, is actually compiling a propagation. If people are interested in these techniques, I refer you to the books on functional programming, mostly being written in England these days. Functional programming is about this, and well-behaved functional programming languages have the property that you can take any computation that has variables in it, and through a fairly simple compilation, change it into a network that has no variables whatsoever, but simply routings for values. Does that sound, please interrupt me if that doesn't sound reasonable. Does that sound reasonable? It's intuitively reasonable, isn't it? Because what is a variable is a place you go to get a value. But of course what you really need in a computation is simply a value delivered. You don't need the value to be anywhere except where the operator is. So by using a combination of those techniques, you can actually, remarkably enough, it's always surprising when these things work. You can actually go to a thing that's an extreme generalization of a spreadsheet cell that does an enormous amount of parallel computation, but in a way in which you see none of the interactions yourself. No, because a production system, it's not at odds with a production system. It's not like Ops 5, as an example, which is a production system I understand people use here. It's basically orthogonal to whether there's a production system trying to do things or not. Ops 5 is an example in which you have to order the rules yourselves to a certain extent in order to get efficiency and so forth. And you can think of this as something which is independent of whether there are rules or not. I didn't say there are rules here. What I said is that what we actually are interested in is whether there's a set of conditions that can deliver to me what I actually need. One of the things you could implement with this idea is a production system. But it isn't particularly like a production system. You could implement a production system using the idea, though. Do you understand? I'm saying, just want to, because some production systems have to be executed in. Sorry, we're getting killed for time. We only have a half an hour, so what I'd like to suggest is that we just sit still while they change the tape. Is that okay? Should only take them 10 seconds. Was brought up about what do you do with real time, in fact, what do you do with time? And historically, the first object-oriented programs that were done outside of machine code were done in a programming language called Simula. And Simula had this way of looking at time. The Simula you had a bunch of objects one for each entity that you're trying to model. So these guys might be modeling pipes. And so forth. And the blue guys might be modeling reactors in a chemical plant or something like that. But basically, as far as Simula are concerned, they're all objects. They're all trying to execute at once, trying to get to the new, trying to advance the entire system time. And they had this problem of, if you have a system time, the system clock that's going on, how can you compute? Because you might actually run out of time for computing before you can actually advance to the next system time. So what the Simula people realized that they wanted to do was, in between the system clock, so the system clock might be 1, and the next time any of these guys had to compute was 2. So what it would do is it would do all of the computing in between the ticks of the clock. So the computing was actually outside the space of the simulation. So Simula, this is a non-real-time situation. Simula running on a mainframe would compute an arbitrary amount in between each state change. So it would guarantee that each, as much as it could possibly do, it would settle down the state of each one of these objects during this time when they were all in process. And as soon as that had happened, then it would say, okay, now I can go to the next time on the clock. It is now 2. What do I have to do now? Then the clock would be frozen. It would compute like mad again and advance the clock again. Now, of course, there's a huge conflict. That's the way you generally do it when you're doing object-oriented programming. Huge conflict between this and when you want to do real-time things. Because real-time things, you don't get to stop the clock. The clock is moving along. And, of course, one of the answers is if you don't have enough computing power to compute before the next time the clock ticks, then you're dead anyway. Okay, so let's assume that we have enough computing power, and just to ask what we can do in object-oriented design to reconcile what time actually means. And the way people generally think about time in object-oriented programming is time has entirely to do with who can view what when. So it's a viewing operation. So let's suppose we have our objects here, and we have some views. Attached to the objects. We can ask, what is it like if one object is viewing another? The first question I just should ask everybody, because this is absurdly simple once you see it, but the first question is, when should I not be viewing the object? When it's in transition. Right? So it means I have to have at least a 2-phase clock. So the object really has two states it's going in. One is it's trying to settle itself to what it thinks is a stable state, and the other one is one it's going to allow itself to be viewed. Okay, so we can do that in a sort of a diagram here. So here's the object and here's the view. So what we're saying is that when the object is computing, we can't view, and when the object is viewing, we can't compute. So we're going to have a bunch of these little phases like this. Now, that's not always useful. Sometimes this viewing thing is very long. So the viewing can actually hold up the progress of the computation. And so what can we do there? This is suggested by actually this model so far. Just curious to see if it suggests anybody. What would be a good thing to do if to break this rigid synchrony we have? What can we do?
Instance at that time, view it later.
Yeah, we could. That's what's called slippage. So we could actually arrange a slippage model. So we let the, as we had before, we let the object compute, and what we take is a copy of it that we let the viewer view. And so the object in simulation can have quite a number of phases as it goes along, and every once in a while we get to view it. So we take, let's say we take this guy right here. Okay, now what's interesting is in an object-oriented system, this slippage model is usually computed automatically by the object and the view, both of which are objects. When you hook the view up to the object, what they do is exchange information, because one of the things that the object has some sense about is how long it takes it to settle its state typically. The view has some sense about how long it takes to abstract the view, and so they actually arrange and build a little buffer in between themselves, and that buffer has the actual amount of information to allow the slippage to happen. So the way this intertwines with doing real-time and deterministic computing is almost all real-time solutions to queuing problems, knowing some sort of determinism, they actually aren't completely deterministic. What you usually do is you're saying, I have some limits that I want to guarantee the computation is going to take place in between, and I'm going to do enough buffering to make sure that those limits get done. So for instance, when you're doing real-time reading of records from fast disks and so forth, you set up buffer areas because you don't want to have real-time constraints in every part of your real-time computation. In an object-oriented system, these are usually handled by having what's called a viewing model. Smalltalk has one called Models, Views, and Controllers, which is quite general and has the facilities in it for generating all manner of slippage models in between by you putting on the outside what it is that you actually need to know from these objects. At some point, of course, you can break it down. There's no real-time system you cannot break down, but this gives you the maximum amount of automatic buffering that the system can generate without having to be explicitly programmed.
Well, relating this to the, like your print instance for each object,
Yeah.
I guess what bothers me is that eventually you have a single device that you're going to have to somehow, in the sense of a concurrent model, that you're going to have to interface with. You're going to have some type of semaphore protection or something. To use this, I mean, as the system grows, it's very, very large. How can these views, in a sense, understand? Do they have to understand all the relations with the other views?
Yeah, well, the way that's usually done is by trying to, again, it's not, this stuff isn't a panacea, but what you usually try and do is when you write a device driver in an object-oriented language, what you try and do is ask what devices are likely to be like this device. What is this like? So when you write, when people do a user interface in an object-oriented language, usually they don't write a driver for the mouse or for a tablet or anything else. What they come up with is an abstraction of what it means to, it's usually called a PIC device. It's an abstraction of what it means to be able to do selection and tracking. And then one programmer at one time writes code for that. And then if you come up in a system and it has a specific device, you may have to write a line or two of additional code, but it's written in a subclass below that. The main driver has already been written, and it's not just, doesn't just serve as the code for what you're doing, it serves as the model for how you treat the actual devices when they're put in there. So part of the charm of the system is to be able to get away from the particular as much as possible and program as much as possible in the general case. And the whole act of subclassing is basically saying to something, I want something just like you except. And the theory behind this, which seems to work, is that it is much easier to program differentially than it is to program from scratch. It's much easier if you see something that is like what you want, and you can get it in a way that doesn't damage anything else. Then if all you can have to make is incremental changes to it, then you should be way ahead. That's not always true. You know, there are always pathological cases. But generally speaking, like this is an example where the whole strategy, once it was thought out, was realized, oh yeah, this is something we can use. It's not just for user interfaces. We can use it for every kind of device drivers. We can use it for every kind of real-time stuff where we have two different clocks going at two different rates and we're trying to synchronize in some way. Why should we have to write this over and over again? Why should some programmer have to figure it out over and over again? It's not that we have the solution to every possible problem, but what we're saying is we've got a solution. It's the 80-20 rule. Get a solution to the 80th, 80% of all the code you're ever going to have to write. If you can put that into a superclass and then distribute it automatically as part of a solution. So Smalltalk, when you're doing a viewing operation in Smalltalk, you don't even have to think to yourself whether you should worry about synchronization or not until long after you may decide that you need it. Then you discover, oh, it's already in here. I just got it for free when I subclassed class view. People try and think about it. Like I say, in Ada, it's a little bit harder because you can't do those superclasses that have all those goodies lying in there. You can do it with a macro operation. And people do superclassing in Ada by making macros that allow them to do a kind of copying and stuff. No. Well, in Smalltalk, no. Smalltalk allows you to basically Smalltalk has no concept of loading code. So everything is there dynamically there, and at any point you can go in, examine any piece of code in the system, you can rewrite any piece of code. In a production case, you really don't want to allow just anybody to go in and rewrite a superclass because of course, it's really bad if the superclass starts doing something different. Generally, when people go to rewrite a superclass is to improve the algorithm that hundreds of applications are already using. Like you may go in and improve the sort algorithm. Yeah. Right. That's why I was talking about the configuration. See, my belief is that in a production case, you must have something like the configuration set up, or else it's just too fragile. It's fragile in a funny way, because in Smalltalk, we used to give $5 bills away to anybody who could crash the Smalltalk system. It's very hard to crash a good object-oriented system because there isn't anything you can get to where you can actually hurt more than one layer of thing. And then the system says, hey, wait a minute, what are you doing? Like in the Smalltalk debugger, as you'll discover, I think there's a tutorial coming up, anytime there's any kind of an error, the system doesn't crash. There's no concept of crashing. The error is simply set aside as just another process. And once when we were debugging the system, we found 1,700 suspended errors waiting for somebody to take care of them. And Smalltalk didn't care, you know, it's just an error comes up, fine, you know, set it aside, it's right there, you can go back to it anytime you want, but keep on running. It just keeps on running. So that's one of the reasons why we didn't do a configuration language, because we were programming in the small and you couldn't hurt yourself. So it was the worst you could have happen was something annoying that would come up, but it wouldn't crash what you were doing. So somebody would fix it or make a note of it. But I think that's intolerable in the production sense, where you really don't, where you have people who aren't part of the same group and so forth, that you really have to have a configurations language. And the superclasses are the ones that you want to have most understood and most nailed down. In particular, for instance, in Smalltalk, it's often to make things like the sorting stuff parametric, so that you're actually sending in sorting objects that will do sorting for you as parameters, rather than even putting that in, embedding that into the code, just because you don't want somebody to try and change it that way. You'd rather have it be something separate that you can dynamically bind in. Really good superclasses don't do much except act as really good binding mechanisms for other stuff that's going on. Yeah. Yes, there is. You can, again, the original Smalltalk, for example, didn't use a kind of procedure call in order to send. It really acted as though you were on a network. And if you're interested in what order things had to be done in, they could actually be stamped and requeued at the other end. And people do that. When you run Smalltalk over a network, people make the connection to the network by having what are called phantom objects. And a phantom object is a stand-in from the object you're trying to send the right, because you're always sending a message to something. So suppose you're so if you're over here and you think you're sending a message, what you think you're doing is sending a message from object A to object B, but they may be on different machines. And so what may be really going on is object A is sending a version of object B, which is really going over the network to the real B. Okay, these are called phantom objects, and usually there's just one class of them. And whenever you're distributing a computation, usually the environment for the objects it just consists of a few local objects, and the rest of them are phantom objects. The phantom objects take care of all of the network stuff and synchronizations and reorderings and other kinds of things that you have to do when you're going to slower media. That's a well-established technique. In any good object-oriented language, you can set that up literally in an afternoon to do. It's quite instructive to think about what it means not to send just a message, but to send an object from one place to another. What part of its environment do you have to bring along with it in order for it to be understood? See, in theory, sending an object, let's say we send objects C across, well, C may not be terribly understood on the other side. On the other hand, it's still active. So if your network has the rule, as ours did at Park, that whenever an object shows up and its class isn't there, its class, a clone of its class, gets sucked over with it. So you can compare that to sending a data structure, which is sending bits, and how fragile they are because you're not sure that there are procedures at the other end to know them. Here you're ensuring that either nothing at all happens or the right procedures are actually automatically sent along. And so you can, remember that story I told in the beginning of the Burroughs 220? That's exactly how the training command protected their tapes. You just make sure the procedures go along with them, and it's quite easy using these phantom objects to make that automatic. So you can think of the network of objects as constantly rebalancing itself as to where the code actually is.
You said earlier that in order to reprogram the object-oriented language to think so large, you need a configuration.
I believe that's true. From Park, yeah, it's been written up. Yeah, well, my message to you is the same. The reason I told you the Arthur Anderson story is they have exactly the same, you know, their attitude to me was kind of interesting. They said they went through several phases, and this is probably, you're in one of these phases right now as well. They went through one phase where the first phase with objects, it was like magic. God, all the things you could do, code is so small. And their second phase was complete disillusionment when they realized that, for instance, Smalltalk, which they were using as a model, didn't scale. They said, you know, what is, you know, is this the emperor's new clothes or what? And I said, no, it's just because part of the reason Smalltalk wasn't built to scale was simply because we were able to do an enormous amount with very tiny programs, and we're designing for children anyway. And when you want to use these ideas in the large, I believe that you have to do a little bit more than you can go out on the street and buy. That's what my message to you is that, and it was to Arthur Anderson, that you know a lot about what once you've learned the object-oriented style, which I believe is the right way of protecting state, the right way of making components, the right way of making superclasses, the right way of sharing. There's a whole bunch of right things about it. In order to make it work in the large, you then have to sit down and protect that by coming up with a configuration language, and you can do yourself a lot of good by doing that carefully, because the configuration language can include languages that you already have hundreds of programmers that know how to write in. In other words, the configuration language can be a way of protecting programs that are already written in COBOL and Fortran, as well as new programs written in Ada. It should be a really separate way. You think of it as the architecture as opposed to the bricks of actually building the thing. The architecture, to me, rules. Life is an architecture. It wasn't as early as the turn of the century. There are people that thought, remember there's this stuff called protoplasm, written about in books. It was supposed to be some special kind of material that you can build living things out of, because people didn't believe that ordinary chemicals you could make a living thing out of. And it wasn't really until 20 or 30 years ago that it was really shown quite definitively that we actually are just an architecture. In fact, we know now that the atoms in our body are actually recycled about every 7 years. So you and I as individuals are patterns in space that material is moving through. We don't have the same atoms in our bodies that we had 7 years ago. We are a pattern. And interesting things are made out of the patterns. You have to have some understanding of the bricks and stuff, which I think everybody is getting now. But at some point, you'll realize that the power of this stuff isn't from what the bricks do, and that the bricks have integrity. The power of the stuff is from the architectures that you can create, and the architectures have just been scratched. Now, up until really a couple of years ago, there have probably been less than God, I don't know, 100 or 200 people over 2 decades actually doing this stuff. So it's the problems that have been worked on have tended to be small. The reason I believe that object-oriented programming works well in the large is simply because it works well in the biological world. And I see no reason why it is going to fall down in any way when we go large. But in order to make it work, we have to either look at the biological world more, which is the biological reason of urging a configuration language, or we have to go after, for other reasons, of just realizing, hey, this stuff gets fragile at this point, what do we actually need? And the answer is a configuration language.
It seems to me that the actual programming of this might be future technology, etc. But I think that there might be some immediate benefit to some of these ideas in what I would call object-oriented design, where you have existing systems that, because of the nature of the islands of automation approach, have gotten tremendously complex. And you need to be able to characterize various things. You can use possibly the concept of objects to help you do that and to help you understand, what are the objects and what are the linkages, et cetera, et cetera.
Right. Well, trying to think of, I think it was Rudolf Serkin that said you can't, if you want to be a piano player, you should spend half of your time reading books. And his point is that if you spend all of your time just learning to move your fingers, you have not absorbed any the context necessary to play any real piece of music. That there's something else besides the practical application of the technique. And I think that somebody was asking me at the break, it was a very good question actually, which is it had to do with sounds like objects make you do a lot of design, but it wasn't said stupidly at all. It was just said, isn't that hard? And I say, yes, it is hard, and it's hard whether you've got objects or not. The main reason is that objects provide both an excuse for designing, and they also give you a framework for holding the design. Every little bit of design you do, you get rewarded in an object-oriented system for having done it. You really get rewarded. Whereas it's hard to get rewarded in a procedure data structure system, because often the design has nothing to hang itself on. There can be local good things, but you can't propagate the design forward the way you can in an object-oriented system.
Doctor, are you saying that we're synonymous with that battalion of programmers or anything right now?
I don't know, because I haven't hung most. Edward de Bono says the problem with most American companies is that when they get in trouble, they redouble their efforts. So, the idea is that we're basically too industrious for our own good, and once we learn a technique, we tend to put our head down and just fight like mad rather than trying to smart our way out of it. Like I said, particular reference to me, I had actually seen these techniques and actually programmed using some of these techniques for 5 years, from a period between 1961 and 1966, before Simula hit me on the head. And it hit me on the head just because at that point I had a problem that was much harder than I wanted to program. That was the first time I was willing to actually see. That was when I was going through and seeing. Then I said to myself, holy cow, this is so, there's just nothing here. All I have to do is this and that. I'm done. All of these things fall in. I was actually programming the game of Space War, which is one of the first video games, but it wasn't even a video game back in the 60s. And there are all of these. It's very hard to do in an ordinary language, because you have all of these spaceships and you have planets and you have torpedoes. And when I was looking at Simula, I was trying to figure a way out of doing this. I didn't want to do it in 30 pages of algol or so. And I was trying to figure out a way, and all of a sudden it occurred to me that every single thing in Space War in Simula was the same thing. The only thing that was different was the costume they were wearing. The planets were the same, the spaceships were the same, the torpedoes were the same. There was like one line of code difference in each of their behavior. I mean, they all had to obey Newton's laws. They all were interacting with each other in exactly the same way. It was trivial, and I wrote that program in a half a page of code, and I've never looked back since. Because that is the thing. And if you don't find this folding up of complexity into simplicity, then either you're working on a truly hard problem, which really do exist, or there's probably a rotation of the situation that you haven't examined yet. You're probably still thinking the old way and thinking in terms of particulars rather than generalities. We're so used to programming up each specific thing that it's hard for us to think of avoiding that, and we only have to program up one general thing and then write a couple of lines of code for each of the particulars, and we're done. That's a really good test in this stuff, and it accounts for the religious fervor of people who have had this happen to themselves, is after pounding your head away on a system, to have it fold up like there was nothing there is the most amazing thing. To have an operating system go away to something that is practically a clock, which is what it is in an object-oriented system. Because what do you need in an operating system? Well, once you've got the ability to sustain objects and stuff like that, you practically only need a clock. You only need to get control routed around, and everything else is written essentially as an application on top of that kernel. That's a very modern way of looking at things, and it's a terrific way of thinking about doing stuff. Okay. Yeah, that's a very good question. Some of these ideas, a relational database, everybody knows what a relational database is, right? Okay. So there are several things. A relational data, an item in a relational database has fields. It has some of the things, and depending on the data dictionary that the relational database wants to sustain, you can occasionally do some integrity constraints. But most relational databases, for example, is very difficult to do the following thing in a data record. And that is make sure that Joe Blow's age is always the right one when you ask it. Because when you ask somebody's age in a relational database, what it expects to do is to go to a field and find a number and bring it back to you. Right? In an object system, what you would have there is you'd send the message age to the object, and it could just go to a field and bring back a number, but a smarter one would actually look at the guy's birth date and compute his age for you right then. And so you'd always get the right answer. Every time you asked age, you would always get the right answer from the object, and you would not get it from the relational database unless you're doing careful updates. That's one difference. The other difference is that in any kind of a relation, it is extremely difficult to embed code, although people sometimes do by embedding it on the outside of the database rather than on the inside with it. So for doing a dynamic simulation, for instance, is quite difficult. A good way of understanding where relational databases is going to go comes out of one of your own products and an industry that McDonnell Douglas is one of the leaders in, and that is CAD/CAM. CAD/CAM can't be done on straight relational databases. There simply aren't enough hooks in there to deal with all of the things. It's not you can't store the data, it's that you can't deal with all the other things that the relational database can't store that CAD/CAM requires. So object-oriented servers like the Gemstone or the ontologic object-oriented servers are ones that the CAD/CAM industry is going towards now. These allow you to do all of the things that you're used to doing with relational database, but also give you this extra level of abstraction that you get from objects. What's nice about it, I think, for people worried about transitions is that there's a fairly reasonable transition. Almost everything gets better when you go to an object-oriented database server. For instance, I think most people would for instance, to have joins be real things rather than a made-up thing for the moment. And they can be in an object-oriented database. Most people would like to have views be things that you can edit back through, or views that you can view. Whereas a view in a relational database is an extremely weak notion of the whole notion of what view is, where in an object-oriented system it's extremely easy to have a view look like the set of stuff itself, and so you can put another view on top of it and cascade them and so forth. And all of those things are being done right at this moment with object-oriented servers. Excuse me? Yeah. I think also because the tutorial that's going to happen in a couple of weeks is going to be one of the people from this Digitalk company, the company that does Smalltalk V. I want to just mention again that besides the fact that it's cheap, Smalltalk V I think is only $99 on the IBM PC and $150 on the Mac. So it's the cheapest Smalltalk. They have by far the best manual. None of the other manuals are even in second place because they actually don't believe that you understand about object-oriented programming in the beginning of the thing. They actually write the manual with a splendid tutorial, hands-on tutorial, for getting versed with all of the object-oriented lore and subclassing and building a very powerful little application. Another thing that they give you for free in with Smalltalk, I don't have any stock in the company. I haven't made a cent on Smalltalk. But what they do is they also give you for free a full-blown implementation of Prolog, Edinburgh Prolog, written in Smalltalk. Okay, and just to give you an idea, this whole implementation of Prolog, written in Smalltalk with its own user interface, its own browser, its own debugger, and everything else, is less than 20 pages of code. Okay, and if you've ever tried doing anything like a programming language like this, is a convincer. Okay, and it uses object-oriented programming for what it's really. It uses the fact, for instance, in Smalltalk, everything is an object. Everything is an object and protected, including the things that you think of as stack frames in ordinary languages that you can't even get to. How is a debugger written in Smalltalk? Well, this stack frame is simply an object, so you simply write a method that allows you to ask the guy, well, what do you have here? What do you have here? Can you advance your PC one? See what I mean? I mean, the debugger is like a page and a half long because it actually is part of, it's just a subclass of class stack frame. Prolog is so simple in Smalltalk because they actually take the stack frame as an object and implement Prolog's control structure directly in using Smalltalk's own stack frames, but using a non-stack protocol, which is what the Prolog backtracking requires. This is gorgeous stuff, and it's done completely without impinging on the integrity of Smalltalk itself. The two systems are integrated together, and so you can do Prolog unifications into Smalltalk variables and vice versa. So it's a perfect example of what an embedded system in an object-oriented system looks like. They give it to you for free. You can do real work in it if you just want to use it. But people are really interested in why this stuff is powerful. That's an example of where the power of it is actually concentrated and used by some design thinking. Here's another one. Most object-oriented languages don't have a complete model. So for instance, when Simula, for instance, has classes, so you have a class paragraph or a class string, but Simula doesn't have classes be objects. Now, if you have an object-oriented language, one of the choices you could make is to have everything in the language be an object. Why not? That means if there are things called classes, there must be a class, a class whose instances are the classes. Okay? Does that sound shaky? Let me just draw it because it's. So I'm going to draw classes in red. So this might be integer, might be fraction, might be paragraph, this might be document, this might be file. And their instances I'll draw in green. So this might be 3, and this might be 4, this might be 3/4, this is a paragraph of text, and so is this one. This is a whole document. This is a whole file. Here's another one. So I have lots of instances of these classes. Then on Simula, these red things, and in Ada, these red things aren't around at runtime. They're like macros. They just help create the structures underneath that these green guys can work with. But in Smalltalk, these are really objects. And the question is if they're objects, what are they an instance of? What is common to all of these things? Somebody tell me. They're all a class, so what's common to all of these? What do they do? They all make instances, right? I mean, they're the thing that holds all of the information that's necessary to make multiple instances. And so you can imagine that there might be a thing called class whose own instances are these guys. Okay? Does that sound reasonable? Why not? Okay, now, remember I can subclass. What do you think it might mean to subclass class? Let me do that. Let me use another color here. So I'm going to subclass class here. Well, just in general, what is a subclass of class going to be able to do? It's going to, no, it's not going to make subclasses. It's going to be able to make classes like these guys, plus something else that I'm going to add, right? Remember, because anything that's of class is going to make classes, so any subclass of it is going to make classes. Now, here's an example of something we did at Park many years ago. We wanted to do a system in which every instance was data-driven. Okay, in other words, we wanted to do a data flow system inside of Smalltalk in which the every thing that happened to some variable in an instance could be propagated to the next thing. That meant that every instance had to have, besides the places in it that an ordinary instance has. Here's what an ordinary instance looks like. It's a thing that has slots in it for holding values. And plus, what we wanted to do was to tack onto that some pointer information that would link all of these guys together so we'd actually have a data-driven network here. Now, how do you suppose we did that? Subclass, class. Right? There are various places I could do that, but what if I did it up here? I put that information in here, and now every class that this guy makes, whatever it is going to have the property that the instances of it, regardless of what these guys are, as I go along making up new classes for this kind of thing and that kind of thing, every one of them is going to have the property that the instances are going to be instrumented this way. See how high that change was made? What I did is I actually changed the meaning of what classness was in the system with one operation. I just subclassed a very, very high level guy, and all of a sudden I got essentially a new Smalltalk with a completely different strategy for how these things, a strategy independent of what the new classes are going to be. Okay, that's the power of this stuff. It's not the direct stuff that you can do that's so appealing now. It's the meta stuff that you can do that's so incredibly powerful. Because you can literally, when you have a new idea that's important, you can literally distribute that idea over the entire universe with just a few changes in a system like this. Well, let's. I think we're about done. Let me give you one of our favorite stories. And there's a Winston Churchill story Winston Churchill jokes always have them at a party after a bunch of whiskeys. And I'm sure everybody knows the one of the, he was incredibly drunk, and a woman came up to him at 2 o'clock in the morning and said, "Mr. Churchill, you're disgustingly drunk." And he looked at her and said, "And you, madame, are indescribably ugly. But in the morning, I will be indisputably sober." So this particular Churchill joke was a little earlier on in the party. He hadn't had quite as many whiskeys, and the hostess of the party came over to him, quite agitated, and said, "Mr. Churchill, I'm just really upset. I don't know what to do. I saw famous Earl over there steal some of my silver salt shakers. What should I do?" Churchill thought for a minute and stuck his cigar in his mouth and went over to the Earl, and along the way he took a salt shaker himself and put it in his pocket. And when he got over to the Earl, took it out of his pocket and said, "I think we've been noticed. Perhaps we should put these back." So that's my version for why we won World War II. In other words, if you want to get people to do something to go along with you, you have to involve them in the same conspiracy. And object-oriented programming is a kind of conspiracy that people are just finding out about it. I hope I've been able to involve you in a little bit, and I hope you'll involve others. Thank you.